Hi students, welcome. In this video we are going to understand about Newton's second law of motion. Here first we will see the examples related to Newton's second law of motion. After that we will understand the equations related to Newton's second law of motion. After that we will see the definition of Newton's second law of motion. So students, here see. First example, here we will take the, suppose this is a ball which is resting on a ground having mass m, as you can see here. When we apply the force of 1 Newton, then the ball will move in rightward direction up to this point, as you can see here. Second, here example is the ball of the same mass here now resting on the ground, and now here we will apply the force of 2 Newton. Okay, so after applying the force, the ball will move in this position, as you can see here. As you can see here, both the balls have same mass, but when we apply the less force, the ball will move less force, that is here in this case 1 Newton. The ball will move up to this position, as you can see here. And when we apply the force of 2 Newton, that is more than previous case, the ball will move up to this position, as you can see here. Okay, so here see, less the force, the less the acceleration of the ball. Okay, and more the force, more the acceleration of the ball. That is here force is directly, that is here see, acceleration is directly proportional to the force. And so more the force, more is the acceleration, more the less the force, less the acceleration. Okay, so further example here is, suppose here this is the object having a 20 kg mass. Okay, and now we are here applying the force of 3 Newton. So when we apply the force of 3 Newton, this 20 kg mass object will move in the rightward direction up to this point, as you can see here. This is the green object is here our previous position of the object. Okay, and this here purple is the position when the force of 3 Newton is applied. Okay, now here further see, here again, here this is the object having 40 kg mass is resting on the ground, and now here again we are applying force of 3 Newton, same as the previous case, as you can see here. When we apply the force of 3 Newton on this 40 kg mass object, this object will move up to this point, as you can see here. This green portion is the stationary position before applying the 3 Newton force, and after applying the 3 Newton force, the object will move up to this point, as you can see here in purple object. Okay, so here from these two examples we can conclude that here, when we apply the force on the less mass object, the object will move up to this position. We are here, as you can see here, keeping the force equal and mass are different. This first case has mass less, so it is moved up to this position, and in the second case mass is more, so the object we can move by using the same force up to this position, as you can see here. That is less acceleration is here. So due to the less mass, when we apply the same force, the object will move with high acceleration, and when we increase the mass and we apply the same force, the object will move up to this position having less acceleration. Okay, so here from this we can conclude that here in this case, from these two examples of 20 kg and 40 kg objects, we can conclude that here acceleration is inversely proportional to the mass. So as this is because when less mass, there is more acceleration, when more mass of the object, there is less acceleration. So from this these examples about related to ball and this object, we can conclude that from the first example, about from this ball example, we can conclude that acceleration is directly proportional to force, as you can see here, because when you apply the force, it when we apply more force there is more acceleration, and when you apply less force there is less acceleration. So acceleration is directly proportional to f. We can conclude this from this ball example. Second, here acceleration is inversely proportional to mass. As you can see here, acceleration is proportional to 1 upon m, that is acceleration is inversely proportional to the mass. As you can see here, when mass is less, we get more acceleration. When mass is more, we get less acceleration. So when we combine these two objects, so we two equations, that is a is directly proportional to f and a is inversely proportional to m, we will get here a is equal to f upon m, that is acceleration is equal to force upon mass. So again we can simplify this equation as force is equal to m into a, that is force is equal to mass into acceleration. This is our equation of force. Okay, force is equal to mass into acceleration. So further here, see now, f is equal to ma, that is force is equal to mass into acceleration. We can here write down as force is measured in newton, m is measured in kg, and acceleration is measured in meter per second square. So here see, 1 newton is equal to 1 kg into 1 meter per second square. So here newton is equal to kg meter per second square. This is the unit. Okay, further we can define this 1 newton as here 1 newton is defined as the amount of force required to give a 1 kilogram mass and acceleration of 1 meter per second square. Okay, so further here see, we will simplify this first equation, f is equal to ma. We can simplify it as here, as we know acceleration is equal to velocity upon time. Okay, acceleration is given by velocity upon time, so we have substituted a here by the term v upon t. So f is equal to m into v upon t. Okay, further here see, but momentum m is equal to mass into velocity. Momentum is equal to mass into velocity. So here this m into v we can replace with momentum. So momentum we have denoted as capital M, and mass is small m, and velocity is v. So further we can simplify this as f is equal to momentum upon time is equal to capital M upon t. So here force is equal to momentum upon time is equal to m upon t. So as you can see here, force is here given by rate of change of momentum. From this equation we can conclude that. Further see here definition of the Newton's second law of motion. So see here, Newton's second law of motion states that the rate of change of momentum is directly proportional to the impressed force and takes place in the same direction in which the force acts. As you can see here, momentum upon time, that is rate of change of momentum, is directly proportional to the f, that is the impressed force, and it takes place in the same direction in which the force acts. Okay, so students, in this video we have understood about Newton's second law of motion. Thank you students for watching this video. Like, share and comment for this video and subscribe my channel. Thank you.